Let's start with today's lesson. Today's lesson is today's lesson is quantification. We're going to continue with predicate logic and quantifiers. Okay. Now, yesterday we saw two quantifications with predicate logic. That was for all and there exists. So, what is the connection between quantification and loops? Okay, we saw that for all x and there is the predicate p of x, what it actually means is that for every x in that particular domain, p of x should be true. Okay, so how do we check in coding whether p of x is true for all values? We put it in a loop. If there are n values in the domain, then one by one each value will be taken and it will be passed through the loop to get whether the answer is true or false. In the case of for all x, p of x, only if all values are true, then that statement will be true. Similarly, in the case of there exists x, p of x, we know that at least one value should be true. Okay, so here again through the loop, we check whether out of all the n values, at least one value will give the output true for p of x. Otherwise, the statement there exists x, p of x will be false. Okay, now remember, loops are have to be ended. It cannot be an indefinite loop. So the domain should be finite if we have to use looping to check for all x and there exists x. Okay, now we are going to look at restrictions. If you look at this, so far we have been looking at for all x px. Okay, and if we say x is of the domain real numbers, all real numbers are part of the predicate statement. Okay, now we are going to restrict the domain. So we have statement, first statement is for all x less than 0, x square is greater than 0. Okay, so the precondition is x less than 0, where x is a real number. Okay, and the predicate is x square greater than 0. So the condition is actually only if, if x is less than 0, that implies that x square is greater than 0. So the condition can be written as for all x, x less than 0 implies x square is greater than 0. Whether it is true or false, we will look at later. This is how a restriction is written. The domain is real numbers, but the real number domain is restricted to only those values which are less than 0. And here, if you look at the next statement, it is for all y not equal to 0, y cube not equal to 0. So now the domain of real numbers is restricted to only non-zero real numbers. And again, for the for all statement is an implication. If y is not equal to 0, then it implies that y cube is not equal to 0. Okay, so we have the universal quantification when it is restricted. It is equivalent to a universal quantification of a conditional statement. So for all y, and then you have a conditional statement. Whereas there exists, when that is being restricted, it is an existential quantification restriction. There, we have an existential quantification of conjunctions. So the two statements, z greater than 0 and z square is equal to 2 should be satisfied. That becomes the predicate. So let's look at precedences. The quantifiers have highest precedence. So before doing an and or an or anything else, we should do for all and there exists. Okay. Now let's look at binding variables. Binding variables means, see these values x for all, if I say for all x, then X is bound to that particular predicate statement. Okay, so that is called the binding. The how far is a particular variable bound, that is a binding variable. Let's look at the example and then we will go for the theory. Okay, look at this statement: there exists x plus y is equal to 1. Here there exists quantifier is binding the variable x. So whatever is the domain of x is applicable to different values of x which is taken by the predicate, but y is not being bound by the quantifier. Okay, so essentially y should be, every time I do a checking in this particular statement, y must have some constant value. Even if it is a variable in other parts of the program, in this statement there should be one value which is applicable to y. Okay, so now let's look at the scope of the variable. Look at this first statement. Let's look at the whole statement. There exists x, open bracket, p of x and q of x, close bracket. So this there exists x is binding both p of x and q of x. Okay, and then we have the statement or. So this there exists does not apply to the rest of the statement. Or for all x Rx. This for all quantifier is only applicable to Rx. Okay, so this x and the first x are essentially not the same. So it could have been written as a different, this for all x Rx could have been written as for all y Ry, because this, the range of there exists does not actually come to Rx. So the scope of there exists x is only within Px and Qx, and the scope of for all x Rx is only within Rx. Okay, and since these two are not overlapping, this could have been represented using another variable. Now let's look at what is a binding variable. When a quantifier is used on the variable x, we say that this occurrence of the variable is bound. So there exists x, or for all y is the quantifier is binding that particular variable x or y. An occurrence of a variable that is not bound, like the first example we saw over here, y, that particular occurrence, essentially it is equal to a particular value or a value that has been set earlier. And that is why that particular variable in conjunction with the quantifier is a free variable. Okay. Now, the variables, all the variables in a preposition should either be bound to a quantifier, that is the universal quantifier or existential quantifier, or the variable will be assigned a value. That means it will be a free variable. Okay, and the scope of the quantifier is within the logical expression to which the quantifier applies. Okay, anything outside the quantifier's scope will be a free variable. Okay, now let's look at equivalences of involving quantifiers. Okay, equivalences involving quantifiers. Just like earlier, we can use truth tables to show that two equivalent statements are equal. Other than that, we can also use proofs. Okay, but it is an if and only if statement. So, disregarding what the particular predicate of S is or the particular predicate of T is, even when we change the predicates or the domains, it should be changed throughout, of course, the statement should be equivalent. Only then we can say that two predicate logical statements are logically equivalent. Now we're going to look at the example over here. We show that for all x, open bracket, px and qx is equivalent to for all x px and for all x qx. Okay, so first we'll start at the left hand side. For all x, open bracket, px and qx. If an and statement should be true, then px should be true and qx should be true for all the x values. So if I have got a value p of a and q of a should be true, then p of a should be true and Q of A should be true because 1 and 1 is equal to 1. Okay, remember the truth table of AND. So in that case, we have established that for this to be true, for the left hand side to be true, P of X should be true and Q of X should be true. Okay, so in that case, if P of X is separately true, it means that for all X, Px is true. And if Q of X separately should be true, it means that for all X, Qx should be true. Then in that case, the right hand side is also true. And using similar logic, we can prove from the left hand side to the right hand side. It's shown, given over here, you can just check it. So these two statements are equivalent. Okay, now negating a quantified expression. Okay, we are looking at an expression in the English language. Okay, essentially, negating a quantified expression is simply using the De Morgan's law. In the De Morgan's law, if I have for all x px and negating for all x px will be for all will become there exists and px will become not px. Okay, so the statement every student in your class has taken a course in calculus. Px is X has taken a course in calculus and the domain is all students in the class. Okay, so the statement will become for x px. And negation of for x ps is, if you look at this, every student in your class has taken a course in calculus. Not all students have taken a course in calculus. Or we can say there exists at least one student who has not taken a course in calculus. Okay, so the statement essentially becomes there exists x, not px. So you see, for all x px negated is there exists, not px. Similarly, you can see this statement, there exists xqx. There is a student in this class who has taken a course in calculus is actually there exists x qx, where qx is x has taken a course in calculus and again x is the domain. The domain is the students in the class. Okay, so the negation of this is again there exists will become for all and qx will become not qx. So the statement will be every student in this class has not taken calculus. Okay, so we can see over here negation is simply De Morgan's law. There exists will become for all and positive will become negative. Okay, these are some examples. First statement is there is an honest politician. So h of x is an honest politician or x is honest politician, let it be there. Okay, and x, the domain x is all politicians. Okay, so the statement is there exists x, h of x. The negative of this will be for all x, not h of x. So the statement will be every politician is dishonest because it is actually there exists a politician that is not honest. Okay, so it means negative of this is for all. So for all x, not hx is every politician is dishonest. Similarly, second statement, let c of x be x eats cheeseburgers and the domain is all Americans. So the statement is for all x, cx. So negation will be there exists an American who does not eat cheeseburgers. So there exists x, not cx. Okay. Similarly, when we negate these statements, for all x will become, the first statement, for all x will become, there exists x and not x square greater than x will become, not x square greater than x means x square is less than or equal to x. So the statement is there exists x such that x square is less than or equal to x. Similarly, there exists x, x square is equal to 2 will become for all x, not x square equal to 2. Not x square equal to 2 is x square is not equal to 2. So the statement is for all x square not equal to 2. Assumption is that the domains are the same. Okay. Now let's show that these two statements are logically equivalent. Okay. So first, let's look at the equivalence of Px implies Qx. Px implies Qx was not Px, not Px or Qx, right? Let's just go back and look at that statement here. Okay, see, P implies Q is not P or Q. Okay, so using that, we need that for this particular, sorry, yeah, here. Okay, so we begin with the left hand side. We have to show their equivalent. So we have to show that left hand side is equal to right hand side, and similarly, we should be able to show that right hand side is equal to left hand side. So begin with negative for all Px implies Qx. According to De Morgan's law, negative of for all x will become there exists, not Px implies Qx. Now Px implies Qx was we saw earlier, not Px or Qx. So not Px or Qx, when negated, it becomes Px or becomes and Qx becomes not Qx. Okay, so this whole statement's negative is Px. That means this conditional statement. Please look at the arrow. This conditional statement effectively becomes Px and not Qx. Okay, and we saw that for all becomes there exists. So we have shown that the left hand side is equal to the right hand side. Similarly, we can show go backward, use same steps, but going backward will give you from the left hand side to the right hand side. So these two statements are equivalent. Okay, now let's move on to translating from English into logical expressions. We saw this already many times. We saw the reason for why logical expressions are required. All are similar logical expressions. When we convert a statement, a natural language statement, into a logical expression, the aim is always to be able to manipulate it easily. Okay, so when we produce a logical expression, the goal is to get the smallest useful logical expression for whatever our need is. Okay, examples. Every student in this class has studied calculus. Every student means we are going to use the quantifier for all x, and the domain x is students in this class. Okay, so the statement C of x will be X has studied calculus. So this whole statement, every student in this class has studied calculus, can be represented using for all x, C of x, where the domain is students in this class. Okay, if we change the domain, instead of having the domain as students in the class, if we just have the domain as all people, then we have to add something else over here. The statement becomes for every person X. If the person X is a student in the class, then X has studied calculus. So we have a conditional statement. So now the statement becomes for all X, S of X implies C of X, where S of X is a student in the class, and C of X is X has studied calculus, where the domain is all people. Okay, not just the students in the class, all people. Okay, same thing, since we are saying that a particular student X has studied a particular subject calculus, it could have been written as Please look at the arrow qx comma y. Here qx comma y, where y is a particular subject and x is a particular student. And since we are interested only in calculus, our statement will become for all x, sx implies q x comma calculus. Okay. Now we have another set of statements again to be converted into predicates and quantifiers. I will do the first statement, you can do the rest. Some student, when you say some student, it is not the for all quantifier, it is the there exists quantifier. Some student in this class means the domain is students in the class. Okay, so there exists X where the domain is students in the class. X has visited Mexico. So the statement is X has visited Mexico. So we have there exists X statement M of X where the domain is students in the class. Okay, similarly try to do the second statement. Now let's look at quantifiers for system specifications. Okay, to again just treat it as an English language statement. Every message, mail message larger than 1 megabyte will be compressed. Okay, so every mail message means the quantifier that we are going to use is for all. Okay, so for all mail messages, okay, we have to check whether if the message is larger than 1 megabyte, then it will be compressed. So we have a conditional statement. Look at the statement over here. Look at the arrow, please. For all M, where M is all mail messages, S M comma 1, if the message is greater than 1, it implies that the message is compressed. CM. Okay. Similarly, do for the second statement. If a user is active, so again, there will be a conditional statement, at least one network link will be available. So there are two there exist. This is also if a user is active. So there exists a user that is active, then it implies that there is at least one, there exists n which is available, n comma available. So look at the statement. There exists a user u, AU, that is which is active. It implies that there exists a network link n which is available. Okay. Now we are going to look at reasoning. One of the reason that predicate logic was used instead of propositional logic is that we can include reasoning into the predicate logic. Okay, so let's look at these three statements. All lions are fierce. It is a statement of fact. Okay, some lions do not drink coffee. And the third statement is some fierce, that is from the first two, we can conclude that some fierce creatures do not drink coffee. So let's first make simple predicate statements. Okay. Let X be lions. So X is equal to, the domain is lions. P of X is fierce. Q of X is X drinks coffee. Okay, the statement is do not drink, but it means that some lions do not drink coffee means that some lions drink coffee also, right? So X drinks coffee is Rx. So now we have three predicates. P of X is X is a lion, Q of X is X is fierce, and R of X is X drinks coffee. Okay, then how will we represent the statement? All lions are fierce. For all X, Px implies Qx. So if X is a lion, then so that means we are taking the domain all creatures. Okay, not just lions. all creatures. So P of x implies Q of x for all x is the first statement. There exists x, P of x and not Rx. That means there exists lions that do not drink coffee. The third statement is there exists x, qx, because here it is not, third statement does not mention lions, it just mentions fierce creatures. So we are saying there exists creatures who are both fierce and do not drink coffee. So these are the three statements. Okay, now why have we not used P of x implies not Rx in the case of the second statement? Because in the case we have said that P of x, we have not used P of x implies not Rx because this particular statement, P of x is a lion and implies, if it is a lion, it implies it does not drink coffee, it does not hold. And if it is a lion, it drinks coffee also does not hold. So the implication will not work for not Rx or for x or for Rx. Okay, so what we are saying in this particular statement is there are some lions which, some creatures, sorry, which are lions and do not drink coffee. So that's the reason why in both the second and the third statement we are not using implies. Instead, we are using the and predicate, or the logical statement is and. Okay, similar to the earlier ones, write the predicate logic for all hummingbirds are richly colored, no large birds live on honey, birds that do not live on honey are dull in color, hummingbirds are small. Okay, so from the first statement, let's just say that x is a hummingbird. So P of x is a hummingbird. And then let's say Q of x is large. Okay, then the third statement, there are multiple statements with lives on honey, so x lives on honey. And then the fourth statement, no large bird and r small can go in together, just negative and positive of the same statement, so that does not need to be repeated. The last thing that we need is dull in color. So let s of x be that x is rich in color or richly colored. Now using Px, Qx, Rx and Sx, let's represent these statements. All hummingbirds are richly colored. For all x, Px implies, where was richly colored? Sx. Okay, so for all x, Px implies Sx is the first statement. Second statement is no large birds. So Q of x. Q of x is large. So all no large birds live on honey is the same, is the negative of there exists large birds that do not, that live on honey, right? So the negative of there exists x is large because it's negative of no large bird is that the bird is small, and that is negative of qx and rx, where rx is lives on honey. Now, instead of writing it like this, we could have written it as for all x, not qx or not rx, that the bird is not large and it does not live on honey. Okay, because that would also be the same. Similarly, birds that do not live on honey are dull in color will be for all x, not rx. Not rx is birds do not live on honey, and not sx is they are not richly colored. So that statement. Hummingbirds are small. For all x, px implies not large. So, not qx. Okay, so this is how we write predicate logic of the natural language statements. Now let's look at what is logic programming. Okay, artificial intelligence began with coding in Prolog, programming in logic. It began in 1970s. Now we don't see a lot of it. There are other coding methodologies that are being used, but a Prolog program included a set of declarations which consists of either Prolog facts or Prolog rules. And then predicates were specified. Okay, prologue facts were defined using predicates, that is logical predicates, and prologue rules were defined as new predicates using the defined facts. Okay, this was a methodology that was used in 1970, and this is just an example. You don't have to actually learn this by heart. Okay, so consider a prologue program given facts telling it the instructor of each class and in which class students are enrolled. The program uses these facts to answer queries concerning professors who teach particular students. Such a program could use the predicate. So the predicates are instructor P, C. Okay, and there is another predicate enrolled S, C, where P is for professor, C is for a particular course, and S is a student. Okay, so look at this code. When it says instructor Chan, math 273, it means that Chan is the professor of the course math 273. Similarly, Patel is the professor of the course EE 222. Grossman is the professor of the course CS 301. Okay, and then we have enrolled are the students who are enrolled in particular courses. So Kevin is enrolled in math 273, Joanna is enrolled in both EE 222 and CS 301, Kiko is enrolled in math 273 and CS 301. These are all facts. Okay, these facts are used to answer queries. Okay, supposing we have a new predicate, teacher P, S, representing that Professor P teaches student S. We already know which professor teaches which course and we know which student is there in which course. So teaches P, S is actually got from instructor P, C, enrolled S, C. A comma is used to represent a conjunction. So using these two statements, we can find out which student is taught by which teacher. Now, prologue answers queries using the facts and the rules it is given. So this was a rule. This is a prologue rule and these are the prologue facts. So let's see whether we can answer. The query is question mark enrolled Kevin math 273. Okay, so this is a direct question and we just have to look whether the fact is there. Kevin, yes. So the answer is yes. Next query is enrolled X math 273. So we have to look at who all are the students. The question is X. So who all are the students enrolled in math 273? We can see that Kevin is enrolled in math 273 and Kiko is enrolled in math 273. So the answers are Kevin and Kiko. Okay, another query is question mark teaches X Joanna. So what should be done for this? Go back. Okay, we have this rule. So we have to check first in which all courses Joanna is enrolled. So we get the answer. Joanna is enrolled in EE 222 and CS 301. So go back. We have the answer for this side as EE 222 and CS 301. Now we need to look at who were the professors for those two courses. So EE 222 was Patel and CS 301 was Grossman. So when you look at the AND of these two, you will get the response Patel and Grossman. Okay. With this, I want to stop today's lesson. We will do nested quantifiers and a few other topics in the next class. Bye.